The probability of extreme changes in asset prices is significantly larger than what the Black-Scholes model predicts. In fact, the Gaussian does a poor job at modeling details of the distribution of log returns. A possible improvement that stays close to the Black-Scholes framework is to assume that the log returns follow a mixture of two Gaussians instead of a single Gaussian. The PDF of a mixture of two Gaussians is equal to P times the normal PDF of parameters μ1, sigma 1 plus 1 minus P times the normal PDF of parameters μ2, sigma 2. The variable z takes values between minus infinity and infinity. P is the probability of the normal distribution of parameters μ1, sigma 1, and 1 minus P is the probability of the normal distribution of parameters μ2, sigma 2. To generate a sample from a Gaussian mixture of parameters P, μ1, sigma 1, μ2, sigma 2, we first generate a sample from a Bernoulli distribution of parameter P. The value of xi is equal to 1 with probability P and to 0 with probability 1 minus P. The second step is to generate a sample from the normal 0-1 distribution. Finally, we compute z equal to xi times μ1 plus sigma 1 times x plus 1 minus xi times μ2 plus sigma 2x, where μ1 plus sigma 1x is a sample from a normal distribution of parameters μ1, sigma 1, and μ2 plus sigma 2x is a sample from a normal distribution of parameters μ2, sigma 2. The combination is a sample from the mixture of the two Gaussians. In this demo, we're going to generate random numbers whose distribution is a mixture of two Gaussians. In particular, we're going to generate a matrix of random numbers with 1,000 rows and 100 columns. The parameters of the Gaussian mixture are indicated here. The probability of the first component of the Gaussian mixture is 0.7. The mean of this first component is -1, and the standard deviation is equal to 1. The second component, whose mean is 4 and whose standard deviation is 3, has probability 0.3. In this way, the sum of the probabilities of component 1 and 2 is equal to 1. The simulation proceeds as follows. We can use this matrix of Bernoulli P random numbers to generate a corresponding matrix of random numbers that follow a Gaussian mixture in two ways. The first manner is a direct implementation, which we're not going to use, but I'm going to explain it, is basically to generate numbers from component 1 and then multiply them by xi. Remember that xi has 1s with probability p and 0s with probability 1 minus p. So basically this element by element product will give us contributions different from 0 only for the values of xi equal to 1. And these will correspond to component 1 of the Gaussian mixture. Similarly, we'll select by multiplying by 1 minus xi random numbers from the Gaussian component 2. 1 minus xi will have value 1 only when xi is equal to 0. The preferred implementation, however, is these three lines of code. Basically, what we do is use xi as logical indexes. So this basically selects the components of z for which xi has value 1, and this selects the components of z for which xi has value 0. The components of xi for value 1 will come from the Gaussian component 1, and the components of z for which xi has value 0 come from the Gaussian component 2. Finally, we can compare the scale histogram with the model PDF, and we see that the profile is actually what we were after.